Oh yeah. Okay, cool. So I guess we have enough people to get started. And welcome everybody to the AUTOML tutorial. I'm André, I'll be the session chair. I'm going to introduce two of my wonderful colleagues here, Theresa and André. Both of them have been working. I've been working closely with them for now, I don't know, 2 years, 2.5 years. Yeah, and Theresa has worked longer with André even before that. They've been pretty foundational to AutoRL. I mean, we love it so much that we just started AutoRL.org. In case you haven't checked that out, you should. Yeah, and hopefully you guys have a lot of fun with this tutorial and get more inclined towards reinforcement learning and automated reinforcement learning. So please give it a big round of applause for André and then Theresa.
Thanks again for the kind introduction. And yeah, I also wanted to just plug AutoRL.org again. We're trying to really make this a resource where all the interesting stuff about AutoRL will be collected. So check this out. We're working on extending it. We just started. So yeah, if you're also interested in maybe pointing us to resources that we should add, feel free to reach out. But with that being said, I had already given this talk earlier, but just to make sure that everyone in this room is actually on the same page about reinforcement learning. You've seen this slide again, right? Reinforcement learning is all about agents interacting with the world. I'm not going to explain the diagram again. We have that had this morning, but what I'll try to show you here, if the internet holds up, is this small demo of how this actually looks like. Right. So here we have an agent, this purple dot in the top left that needs to interact with its world to reach the goal position in the top right. Maybe let's speed the agent up a little bit. And how it does the learning is by, well, random exploration in the beginning, right? It gets a reward of 0 for every transition, except when it falls down the cliff or when it reaches the goal. Now, already after a few random explorations, you've seen that it found some meaningful policy, and it has an estimate of the reward and basically the cost to go until it reaches the goal state. So that's just really to highlight how these reinforcement learning agents work by interacting with the world. And now I need to go back to this one. Zoom is in the way. Oh. It's opened the same link twice. Perfect. No, I don't. Again, you've seen a similar slide like this twice already today, but there are some different examples here. Don't need to talk about DQN again. I don't need to talk about drone racing again. But what I also wanted to highlight is car racing. Right, there was a very interesting paper by Sony AI where they actually applied deep reinforcement learning to take control of a racing car in a video game, and they could actually beat the best human players. And it's a very high fidelity space, so I thought to really highlight this. And to just give you an idea of how these inputs, these observations of a state look like, here are some examples of like what it looks like in Atari games. You actually learn from these raw observations, the pixel observations. And in the DQN paper, right, everything was just scaled down so that it is manageable to deal with, but it was sufficient to actually learn meaningful control and outperform human players. Now, if we talk about this car racing example that I mentioned by Sony, where this car is controlled by an AI and this car is controlled by an AI, and this is one of the best human players, right? You might ask yourself, is this now also trained on pure pixel observations? And the answer is no, kind of, sort of, but there is lots more engineering going on in the background to actually make it work, right? And even if we have a very laggy version here, what you can see now is the car goes for an overtake, and in a similar situation, a human player would have likely lost control because the car was already starting to wobble. But the RL agent actually learned to exploit this behavior to really overtake humans when they are not as daring as the RL agent can be. And last but not least, because I really like the video of the racing drones, to really show you that this can also be applied in the real world. Again, slightly laggy. The blue drone is the AI drone, and the red one is the human drone. And one thing that you saw in this slow motion is the AI, of course, could react much faster to the go signal, but also it's possible for the AI to just take tighter turns and just really optimize the trajectory that it's going through. And this example, again, is really to highlight that RL does not have to be constrained to simulators, but it often requires lots of simulation to be able to be applied into the real world, right? And then if you set everything up right, you can close the sim to real gap and use reinforcement learning in the real world. But I have hinted at this already a little bit. All these examples that we've seen used lots and lots of domain expertise, right? There were huge teams sitting there, just setting their agents up, tuning their agents, deciding how the state space should look like, deciding how the reward function should look like, deciding on the fly how hyperparameters might need to be changed just to make it work. But if you don't have all this expertise, often you just run into the wall and can't get reinforcement learning to work, right? And not all of us have the time to just spend weeks or decades on tuning RL agents until they finally do something meaningful. So that's why we should automate them. And there's this paper from 2018, the Steep Reinforcement Learning That Matters paper by Henderson et al. That really was a wake-up call for the community, where they showed that RL is sensitive not only to hyperparameters, but also the network architecture, the reward scale, the random seeds and trials, the environment type, as well as code bases, right? So there are lots of elements that you could optimize to actually get your RL agent to work. And just to show you how this environment type influences already the reinforcement learning problem, let's look at very similar environments and compare some algorithms on it. And that's an example from this 2018 paper. So in this hopper environment, where, as the name suggests, a small robot needs to learn to hop, the TRPO and PPO algorithms perform extremely well. But the DDPG algorithm is really outperformed, has a super noisy reward curve, and just doesn't get to the same performance as the other algorithms. In the half-cheetah environment, all of a sudden, DDPG works extremely well, and TRPO and PPO don't work that well, right? And remember, it's still from this Mujoku simulation, and while you don't have to hop with your robot in this case, the transition dynamics are not that dissimilar, and the goals are also not that dissimilar. But just changing the algorithm that you use can give you great performance or really bad performance, right? And if you recall from my talk earlier that it's expensive, just playing around and figuring out, oh, which algorithm should I actually use, you waste a lot of time. And just as a third example, here the Walker environment, again, flipping things around. In the beginning, DDPG might look good, but then it gets overtaken by TRPO, while PPO is very good in the beginning, and then all of a sudden at the end, PPO and TRPO perform nearly the same. So that's just to, again, highlight that there's even a worse problem, that just over time, things change. So you don't have these very clear rankings necessarily as we had in the other examples. Okay, so how should we then choose a reinforcement learning algorithm for our problem at hand? And well, the reinforcement learning community is not at the stage where they're automating everything. They're now still trying to define heuristics. There's the example from, I think, an Intel RL library, where they had this small set of questions that you could answer to figure out which of the possible implemented algorithms you should actually use for your problem. It was a very porous heuristic, but at least it gave you some guidance of which algorithms you should try or you shouldn't try. This code base is discontinued by now, but there was a recent paper, a 40-pager on archive, which is basically suggesting a bunch of questions to ask to figure out which RL algorithm to use. And if you were to now go to this RL Picker website that they created and answer the first question about feasibility of learning the transition dynamics of your environment, then there might be a follow-up question of you being interested in data efficiency or not. But if you answer that, then the RL picker will tell you, well, actually, you should use something model-based, but this is not covered by this RL picker. So please just look into a survey paper. And this is not me saying that the RL picker doesn't give you good suggestions. It's just me telling you it's impossible to come up with a heuristic that covers all of RL, that works for all possible environments, and will be still true in the future, because there's so much progress happening in RL at the moment. And what I really also like to highlight here is the discussion and conclusion section from their paper. They said from the sheer number of tables and algorithms in this paper, it's clear that there's no silver bullet, right? That's the yellow part here. And we in the AutoML community kind of know this already, because we have done all algorithm selection and all other kinds of automating machine learning techniques to deal with these problems. But what they're also doing here is suggesting that, well, actually, we could just ask a subset of the questions, intermediary, test these questions if the answer was actually, or the hint of this heuristic was actually right or not. But in essence, what they're doing is highlighting that you should iteratively test your hypothesis if it's correct, and then maybe stick with this choice of algorithm or switch to a different algorithm. And that's something we, of course, can automate. And that's what we're doing on the AutoML community. And again, recall this paper is from 2024. So it's not an old paper. The RL community is still struggling with this algorithm selection problem. But now that we have looked at how we can actually choose an RL algorithm, let's look at what makes the problem even harder. And here we need to look at the hyperparameter landscapes. So for this, I need to recall your attention or focus your attention on this problem, that learning is done by iteration. And you know, learning in a supervised learning manner in this fashion, you initialize your model, you fit your model to the data set, you observe the model performance, this gives you a loss, and you tend then to use the loss to update your model, right? That can be just following some gradient and so on, but you repeat these steps until your training budget is exhausted. If we look at reinforcement learning in a similar manner, then we initialize a policy, we generate some observations, we get the performance of the policy that gives us a loss, and we adapt our policy based on the loss. And again, we repeat this until our training budget is exhausted. Now, it looks very similar, but there's one crucial difference here. The word generate, right? We're not dealing with a static data set as we're doing in supervised learning. We're dealing with changing data. And we're dealing with changing data in an already iterative process, right? So we're actually trying to learn something in a moving target. And to highlight this even more, this is the general principle that you see in reinforcement learning, that's generalized policy iteration. So you start with a policy, you evaluate this policy, then you get a model that tells you what is the value of using this policy, right? Is it a good policy or not? That value function you typically then use to find a better performing policy by acting greedily with respect to this value function. And then you get a new policy, which gives you a completely new value function, which gives you a new policy, which gives you a new value function, right? So you have an extremely iterative process here. And don't worry about the details of this equation here, but just to highlight how this looks like in one of the most popular RL update rules in Q-learning, right? You update your estimate of this value function, in this case, the Q function, by taking the old estimate and then following some gradient. So you're used to that from supervised learning. You're also used to this hyperparameter, the learning rate, right? That tells you how strongly you should follow this gradient. But one thing that is different here in this example is the discounting factor, because reinforcement learning tries to optimize rewards over time. And the discounting factor tells you how strongly these rewards in the future should weigh in this update rule, right? A very small update discounting factor basically just gives you a very greedy optimization. And a discounting factor of 1 gives you an undiscounted problem, right? And you really want to optimize for the long-term dynamics. So that being said, in our iterative problem here, the parameters that are being learned are the models of the value function, right? Typically, the weights of a neural network. And the hyperparameters the learning rate, and the discounting factor. In full Q-learning, there are also other hyperparameters involved, but just for the example that we're looking at here now, you don't need to know all the other hyperparameters. And there was a really nice paper by Aditya from last year's conference, where they looked at the landscapes of exactly this deep Q learning example, right? With discounting factor and learning rate. And in essence, what they did there was start out with some configuration and policy, run it for some time, and do this branching and record the performance at these different branching points to see how the landscape evolves over time. And if you do that, then you get a picture like this. In the beginning, you should have a very small learning rate and actually a fairly low discounting factor, right? So you can be a little bit more greedy with respect to the reward that you're optimizing, but you don't need a high learning rate in the beginning. Then in this particular example, it turns out after a while, you should look more at the long-term dynamics, right? Increase the discounting factor, but keep the learning rate low. And at the end, you should have actually lowered the discounting factor slightly again, but increase the learning rate to get the maximal performance possible, right? So just to show you that this iterative process where you generate data on the fly just really lets you move through a very challenging optimization landscape, telling you that you also should ideally adapt your hyperparameters on the fly. And we might do some dynamic tuning in terms of learning rate schedules and so on in supervised learning. But again, it's different from what we might expect here in reinforcement learning because everything is so dynamic already. So just to drive home this fact, HPO for RL has to deal with much stronger non-stationarity than is the case for supervised learning. Right, so if you're interested in applying HPO for RL, you really need to be aware of this problem, or otherwise you might really not get to good configurations in the end. So far, we have talked about choosing the algorithm and its corresponding hyperparameters, but there's more to the RL pipeline. And for that, I want to highlight the RL survey, AUTORL survey again. And in this survey, we had the differentiation between learner tunables, which are on the algorithm level and the hyperparameters, but also the actor tunables with the network and the environment, right? And just to mention something that has not come up yet, you could also do the meta-learning thing and learn the reinforcement learning algorithm itself, right? But we're not going to cover this in this tutorial. Instead, let's now talk about networks and what might be different in reinforcement learning with networks than what you're used to in supervised learning. But first, what is the same thing? Architecture matters, right? Earlier, we have seen already from the 2018 paper, the choice in architecture is important. But often in RL, you can get away with much smaller architectures than you're used to in supervised learning. Of course, you can also use foundation models for RL, and then you are back to huge networks, but typically, we're not doing this in reinforcement learning. And to give you an idea, again, from the 2018 paper, how small networks tend to be, the best network here, in blue, has 2 hidden layers, each with 64 hidden units. If you deepen the network and just add more hidden units, you actually decrease performance. And if you have a still a 2-layer network, but with just wider like with this 400 and 300 layer unit layers, then you really drastically decrease performance. So in RL, you often find these comparably tiny networks that perform really well. And I think that's particularly the case for, it's particularly the case when state features are well engineered. For example, in stuff like Haptita and the Mojoko environments. And thus, this RL setup could pose a really nice playground for neural architecture search, where you just need to, again, be aware of the dynamism that you're dealing with, right? You have this highly iterative process with changing data. So you might need to think of architecture slightly differently than you're used to in supervised learning, or just the effect that the training process has on the architecture. Good. Now, to reiterate what I was trying to say, learning is done by iteration, right? Just recall this fact. But this has an interesting consequence on the networks that we're using in reinforcement learning. And in RL or deep RL, we are faced with what is called the primacy bias. Now, what is the primacy bias? Primacy bias just means that agents are prone to overfit to early experiences. And that negatively affects the overall learning, right? So you're moving through changing data, but you're overfitting to the earliest experiences. And your network is not plastic enough that it can recover from this overfitting. So you're really stuck with the policy that you learn on the earliest data that might not have been so meaningful, not so high quality. Why is this the case? Well, the authors from the paper that I listed here identified two reasons: replay buffers and replay ratios. For those of you not familiar with RL, replay buffers have been introduced to combat the training non-stationarity. In a sense, a replay buffer is just a temporary data set. So instead of just using the data that you generate and immediately training on it and discarding it, you put it in a replay buffer and keep it in a replay buffer for some time. And you sample from your replay buffer so you can train on a sample multiple times. And it just gives some more stability into the training by not immediately always discarding the data and training on the latest data, but training on the replay buffer just gives you the stability. But after a while, of course, you will also discard the oldest samples from the replay buffer so that you not forever train on really old data that is not meaningful anymore. And replay ratios just tell you how sample efficient you are. Replay ratio basically means how often do you use a sample that you generated to update your network or do a gradient update basically. So you can use a sample multiple times, do multiple gradient updates in a row, and this increases your sample efficiency. But if you have a very high replay ratio, right, you are forcing overfitting more and more. But in essence, you want to also have a high replay ratio to learn as much as possible from these samples that you generate. So there's this trade-off that you need to have. And an example that the authors came up with is the heavy priming example, where they collected 100 data points and really primed the agent to overfit on this data. So they updated it for 10 to the power of 5 times just with these 100 samples, and otherwise continued training as normal. And they compared it to a normal SAC agent. So the SAC agent with heavy priming really just overfits. The network does not or loses all its plasticity, is stuck with learning or stuck with what it has already learned and cannot unlearn it. So basically, there are often some connections that are basically lost over time, and you cannot recover from that. If you, in this example, have a very low replay ratio, actually you can do normal learning with the SAC agent. So this experiment was really just to show that this primacy bias can really be harmful in reinforcement learning. And especially if reinforcement learners try to push up the replay ratio as much as possible. You can also think of it more like in terms of supervised learning, like, it's heavy overfitting to a single batch of, in this case, early data. Now the question is the data collected by such an overfit agent unusable for learning, right? Are we losing information by using this overfit agent to generate new data? And it turns out, if you train the same agent twice, first, in this case, with a high replay ratio, you get stuck with an overfit agent to the early experiences, but you were able to do some learning at least, right? So you're not stuck with a random policy anymore. You're stuck with a somewhat well-performing policy, and then you cannot learn anymore, but you use it all the time for generating new and new data. And in RL, there are lots of hyperparameters to guide how the exploration should happen, right? So you generate interesting new data around this policy. And if you then take the data that is stuck in the replay buffer after the full training example, and use it to train a new SAC agent. Already with a filled replay buffer, you have high quality data that you can use if you're not already overfit to this early experience, and quickly warm start your agent and really achieve great performance in the beginning, and even continue learning the whole process through. So you can learn with a high replay ratio, but only if you're not already stuck. So the data that is available is of high quality and really helps you learning. And the simple thing that the authors now came up with is resetting, right? Partial or even full resets are helpful in this case. You have seen it in the extreme earlier, where there's a full reset, where you just train on the replay buffer, on the already well-performing or meaningful data, and just start a new training as a whole. But you do not want to change this over long periods of time, right? You instead want to reset on the fly. So periodically resetting the full network tends to harm performance, because you lose way too much information that is already in the updates, or that has happened in the updates. But if you were to keep only the input layers fixed, but reset the output layers, then you actually get a benefit from this resetting. And what you can then see in the orange curve here is that if you periodically reset, you might have drastic performance drops, but you can quickly recover from that because you're training on meaningful data, and you can actually get to a much better performance than with exactly the same setup, just without resets. Now the question for the AUTOML community could be, when or how often should we reset, right? That is a new hyperparameter that's being introduced. You could also think of different parts being reset at different frequencies. You could also come up with ensembles. So this is something where the AUTOML community could again shine and use their expertise to really improve by using this or addressing the problem of the primacy bias and reinforcement learning. And just to highlight this, there's a related idea where instead of resetting parts of the neural network, you're resetting the parameters of the optimizers, such as Adam, right? The parameters of the optimizers might also be kind of stuck to the process that has happened before and might not be meaningful for later iterations. So resetting these parameters can also give you a huge benefit. And again, the same questions that I posted here could also be posted there. But we have talked more than enough about networks. Let's talk about environments now. And the environment is a crucial part in this data generating process, right? So what could we actually optimize with AutoRL here? Well, one thing is we could optimize or tune the observation spaces. That's something, again, that you might know from supervised learning, where you do some cutouts, flips of the images, or rotations to get more robust networks in the end. And that's very similar what you can do here in AutoRL. But then there are reward functions, right? You also would want to tune your reward function to be the best reward function for the agent that you're actually training. So you could augment your reward function by some terms that are just particularly well suited for the agent that you're currently training. And last but not least, there are action spaces, right? If you have a huge action space, you have an agent that is kind of dealing with a very, very hard problem to solve if it has to choose from a multitude of options to choose at every state. If you somehow can dynamically shrink or enlarge this action space, you can make a very intractable problem tractable all of a sudden. But there's also the possibility of a combination of all of these, right? You could define task curricula, which use a combination of all of these things that you, in essence, just provide your agent with the simplest problems in the beginning and iteratively make the problems harder and harder, such that you actually guide the agent through the learning process until it is able to solve the hardest problem that you are really interested in solving in the end, right? And if you do that, you have a very interesting approach in automating the environment choice, which you typically don't have in the supervised learning setting, except for maybe the observation spaces. But now that I have talked a lot about what makes AutoRL different from supervised learning and why it's exciting and why you should maybe get into the field, Theresa will take over and tell you about some examples of successful AutoRL.
Thanks, André. So yeah, we'll look at 3 examples that are not necessarily this year's NeurIP submissions. Sorry, left the AC on overnight, big problem here. But more represent fundamental patterns that have been successfully extended in the community, have been used to show you what methods look like for RL. And the first one, I think, is already quite different from what you might be used to in standard automated machine learning. It's called prioritized level replay. It's called level because they're literally working with video game levels. So something like Atari. In this case, it's a specific environment simulator called ProcGen, so procedural generation. And what they want to do is, in essence, have something like a task curriculum. So it's a dynamic process of adapting which level you play in which sequence. The idea being that if you start with easier levels, then hopefully you can learn things from those levels that you can transfer to harder ones, where you can make progress quicker. And something that's also interesting to know, unlike a lot of our AutoML processes, this is actually unsupervised. This is an unsupervised gray box method. So what happens is we have an RL algorithm somewhere. I think that's the one on the right where you see train. I don't think this lights up, does it? Yes, it does. So we have an algorithm that trains. This always just trains on the latest set of data we've seen. Those are these T's. And those are 2 possible sources. One is the general level space, where you can just say, I pick any level, and we just say it's random which level we pick. But we only pick a new level with a small percentage, maybe 10% of the time. And the rest of the time, we replay levels that we've already seen. And what do we want to replay? We want to replay levels where we've seen a strong learning signal. This is usually approximated by something like magnitude of the loss, or a change in prediction magnitude. So there's been a few different criteria that have been explored here in the selection process. There are a few options of what you can do here. Combine it with staleness, for example, saying, okay, I haven't seen this level in a while, maybe I have improved. And this way of scheduling, in a, as I said, fairly unsupervised, fairly rough way, is actually massively helpful. You can imagine it, since you probably don't know the simulator, if I would train our robotic dog at home to fetch me a ball, I would start with ball throwing locations that are, well, manageable for the agent. So maybe I start throwing balls that are close, because here I can see it gets closer to the ball, it can actually reach it, I get a learning signal. If I would throw the ball like 500 meters in some direction, the dog might just run around in circles, I get no signal. But the further I get, I throw the ball a bit to the left, to the right, and then repeat those that seem to, let the dog make progress. As I said, this has been extended quite a bit, and this is actually a massively helpful paradigm in reinforcement learning, even though it might seem to someone who maybe mainly works with Bayesian optimization or something to be quite vague. And it actually is, but we don't always seem to require the exactness. In this case, the dynamism of the method is actually more important. Similar dynamic method, but this time for hyperparameter optimization, so maybe a bit more familiar for you, is HOOF. And it's a really, really simple and general loop. So again, we have training, and in this case, it's also partial training. So we say, for example, we train for 1/10 of the runtime. So it's not a massively short amount, but a good chunk. And then we ask an optimizer for some new configurations. This can be any optimizer. We use the samples we already collected to fit those configurations. So we don't need new data. And this is actually the much quicker part in the whole pipeline. So just fitting the data is very cheap in comparison to getting new samples. Then we estimate how good the configuration was and go on. And doing this, we get a schedule of length, in this case 10, that's dynamic, that fits the current state of training, and we don't need to spend any extra interactions on the evaluation. How do we approximate the cost? This is also extremely simple and somewhat vague again. We have collected a bunch of samples, and for each sample, we first look, after we fit with the new configuration, is this now occurring more than before? Are we now oversampling this? Are we undersampling this? Are we likely to see more of that? And then we weigh that by the quality we've seen of the sample, because obviously, if we now see a sample more often that is associated with a really good reward, we want to encourage that. That is a sign of good quality of the configuration. obviously an approximation. Without doing full rollouts, this is quite inaccurate. But again, just having a dynamic schedule as opposed to something like a statically tuned BO configuration can make a massive difference, and it's actually performed quite well. And the last one is probably the most used AutoRL method out there, you could say, even though it is really extremely simple. It's called population-based training. And in essence, it is something like an evolutionary strategy. I say something like, because the mutation operation in the original is literally decreasing the hyperparameter by 20% or increasing it by 20%. That is the full mutation strategy. If you have something categorical, there's a probability that you set as a hyperparameter to resample that. It is really, really much, much simpler than something like DE or CMAES. But it works in a very similar way to what we've seen before. We have partial training. This time we do it, in this kind of case, 4 times, just any population size. And then when we've trained, we have seen, okay, now this population member performed better than another. Let's replace the worst ones with the best ones. So just copy the weights and do this extremely simple mutation. And again, this is extremely noisy, as you can imagine. This is not the smartest strategy ever to adapt hyperparameters, but simply because we are able to get a schedule, this is widely used. And in a lot of cases, at least if you choose a population that's large enough, it does reliable get you really good reinforcement learning agents at the end. You can, of course, also combine these things. And I'm highlighting this with a special section because, as André already said, a lot of different things play into each other. And as you might have seen, intuitively, all of the approaches I just showed you are dynamic and they have some partial training component, but it's not 100% intuitive how you would actually combine them. Plus, I didn't say anything about networks again. And I also didn't say anything about things like meta-learning. Why do we actually want to have this bigger system? In this case, it is because all of these things are actually intimately connected in reinforcement learning, which is unfortunately highly annoying. And given that most successful AutoRL methods are dynamic, highly dynamic in some cases, we need to really pay attention to that, because if we change one aspect, like for example, if I say, hey dog, now I want you to run to the left a lot, then very likely I need to at least switch up my hyperparameters to make the dog actually look in more spaces than it did before. Depending on what it had to do beforehand, adjusting the network might be a good idea, or even resetting it to account for plasticity. And then who knows what else, what other AutoRL systems I have in the loop. I might really need to touch upon everything again. So just having separate methods that do separate things is a very risky business. Again, yeah, I think this is exactly what I just said. Yeah, and that is another thing. The algorithm, I didn't even mention that before, because that is very uncommon, but especially if we use an outer loop method like PBT, it doesn't really care about anything but quality. We could even say, hey, hyperparameters look good, agent looks good. Maybe now we just want a different algorithm. André already said some algorithms just work completely different, even though they all are used to solve general RL problems. But there's fundamental difference between algorithms that, for example, update all the time continuously in really small steps, or algorithms that just want to see a lot of data, update on the whole batch. Those work completely different, and it could make sense to say, okay, now we are at a point where algorithm of kind 1 with small updates works well enough. Now we just want to get a lot of data in parallel, use algorithm type 2. Not quite possible at the moment, or at least not experimented on. Because I can give you one example where this has been tried, and you might see where the troubles are at the moment. So this was a paper from the first AutoML 2 years ago, and it's called Bayesian generational population-based training. So this is one iteration of the population-based training thing. In this case, we don't do the very simple mutation of just multiplying the hyperparameter. We actually use Bayesian optimization in the selection. So here we have basically population that's times that t, and here on the right, it's times that t plus 1. We see here we have a really bad agent, and we delete that. We just override it with a really good agent. And we use BO for the hyperparameter adaptation. What's new is you also see some neural networks here. And these can also be adapted on the fly now. In principle, that's really great. I think this is actually something we want to get closer to, especially for reinforcement learning. But how that happens is A, maybe you override a network if it performs better. This would not give you a lot of flexibility. That's not a good search space. If you only do this 10 times, and sometimes you might not see a big performance difference, that's not efficient NAS. The alternative is you can say in some steps, okay, I actively want to do a NAS step. So what this method then does is take a break from this whole loop, instead goes into an additional step after that, where it runs a few iterations of darts, collects additional samples to then distill these networks into new network architectures, and continues this loop afterwards. This brings a few problems with it, obviously. It's a naive combination of two approaches, and it is a good example that they tried to do this, but what they do ignore is things like in RL, we collect our own samples. That also means we should be careful how we use them. Collecting new samples for distillation might not be necessary, and it might get very expensive if we are working on a real application. Also, we keep reusing the same kernel afterwards, even though we ran a bunch of darts, which might actually result in very different architectures. So maybe we have biased our BO kernel for small architectures. Suddenly we find a network 3 times the size. Will that still work? It's unclear. And in reinforcement learning, we actually have a lot of information. We don't just have the data, which, again, we could use more here. We have a bunch of predictions. We have something like, how did the state develop? Did we explore? We can qualitatively actually say more about what happens in learning than we can in a lot of supervised learning, but it is not frequently used yet. And I believe this is an example of where you can probably go inside the cracks of this method and start reusing a lot more of this information. But this is where we are right now. This combination of approaches is really not common yet because we still struggle with the approaches themselves. There's a good reason for that. And the reason is, as in much of AutoML, evaluation, and also generalization. Generalization is a particularly big topic in AutoRL, even though obviously it's also very big in AutoML, just because there is a huge cost associated to reinforcement learning. Generalization in this case means we train an agent. So we have an environment, an agent, we train that, have some AutoRL system. That's great. What we now want is that this solution actually transfers to some problems that look similar. So here you see, for example, the yellow one, that's quite far away from the original environment. This might not actually work as well. But the blue one, that looks quite similar. So the behavior we want to induce is we want to run this expensive AutoRL loop as few times as we have to, so that we can actually afford it. For many applications, collecting data is extremely expensive. Running the system can be very expensive, especially in academia. And this is really almost a necessity. This one-shot AutoML, where you just train something and then you have a policy and it works. That's very, very seldom in the case that this is practical in AutoRL at all. But evaluation in itself is not quite easy. How do we even determine what is good? Well, first we look at what is good in the RL loop. In the RL loop, we measure something called return. So return is just the sum of all rewards we receive. Then in principle is easy. And in principle, we could say, okay, now we do some partial evaluations. It's a great idea. But for evaluation itself, though, it doesn't quite work because we have this annoying gamma. That's the discounting factor André mentioned before. And this is actually part of the problem specification. So they tuned it because there's an agent view. So if you want to learn in an environment that has a discount factor of 0.9, that means that I want you to act as if there's a 10% chance I stop the environment in the next step. That's the agent view. And from a problem specification view, that obviously means I want you to value future actions in a certain way, right? So we actually do need to look at larger evaluation trajectories. We can't just say, okay, let's evaluate for 10 steps and we get an accurate performance. Generally, that does not work. And the even bigger problem is both parts that contribute to this, both the environment and the policy can be stochastic. So we can't even do one rollout. Likely we need multiple ones. Why? let's look at this. This is something called mini hack. If you've seen NetHack before, this is variation of NetHack. That's quite funny. And here it's called wand of death. So your task is to get this wand that is covered on the left side and then kill that monster. And a great example of environment specificity, great as in it's probably good for the player, would be the monster moving to the right. So you have a bit more time, a bit more space to actually do something. But the monster could also be moving to the left, so closer to you. So you need to repeat this to really cover the monster behavior. If you only do one rollout, you could either get a nice monster or a mean monster. You need to have the mean of those. The same can be true for the policy, because usually we don't see all of this, right? Usually we can't assume that we have perfect information, then we might not even need to do reinforcement learning. What we usually assume is we see it maybe around this much, around where we stand. And from this perspective, actually, this looks like you don't know where to go. So we can be lucky and the agent deduces, I don't know where to go. I could go to the left and we actually get closer to the wand of death. Or the agent decides, let's explore right first. Now, again, can happen even though the policy is the same, because the observations can sometimes not give us clues where we actually need to go. So we need to do long enough rollouts that we actually get the full estimation, including our discounting factor behavior. We need to do enough evaluations to also cover the environment stochasticity and the policy stochasticity. So just talking evaluations, we haven't trained anything in this case. This is already a trade-off between performance and extra cost. And what adds to this is that some return distributions can be quite binomial. So you can't always assume that you get a nice average out of this. Because in this wand of death example, for example, I think in a lot of cases you don't actually see any reward unless you make it to the very end. And everything before that just looks very samey. That means it can take quite a while until you get a really reliable estimate. Obviously, if you want to look at different seeds, which you definitely do, or different task variations, a different corridor, for example, you also need to do the same spiel again for that. And we can even lose quite a bit of information there because commonly we just average, or even do an IQM where we remove the quartiles. So this ends up being quite a costly procedure because we now have this unstable environment, this potentially unstable RL algorithm, and an AutoRL optimizer, for which we also commonly use something that has a stochastic element, right? And now let's calculate why this might be expensive. And we'll start with evaluation cost just for the one RL loop is 1. This is hard to model. This really depends on the environment, how many steps you actually want to see. It could be a simple task that ends quite quickly. It could be very variable. So we just say this is 1. We have this policy pre-trained. Again, we're not training, we're just evaluating. Then we really need to do this across at least 10 seeds. This is very important in reinforcement learning, actually very important reinforcement learning, to a degree where 10 seeds is the lower bound. There are definitely environments where you want to do this 50 times, not 10 times. Then we multiply that with how often we want to see our AutoRL system running. I did this times 5. Times 5 is also very optimistic. This, I would say, assumes that we have a fairly stable system that works quite well and that we can assume doesn't really introduce any crazy behavior into the RL loop often. So it's 50 times for the first task, and then 50 times for every other task we want this configuration to perform well. That's just the evaluation cost. That's without retraining anything or tuning anything. And that really causes a big problem in this research space. Because I would say up to maybe 1.5 or 2 years ago, reinforcement learning was really deathly expensive for academia compared to supervised learning. This has gone down a bit. But what has happened is that due to large evaluation costs, obviously comparisons have suffered. And we can see that really well in HBO for I think HBO is a really good example because you cannot escape HBO, right? I mean, whatever you use in machine learning, you have hyperparameters to look at, you have hyperparameters to tune. The same is true for RL. So apart from, I think, environment design, I would say HBO is the biggest part of AutoRL methods. A lot of people are obviously interested in having good hyperparameters. So what's the basic fact about RL? As in many algorithms, we have many important hyperparameters. This links to a paper where you can see a lot of plots. For now, you'll just have to believe me. There are many. Most of them are important in some way. And what I will show you a plot for is which of these matter actually is super domain dependent. And this is an example. These are two toy problems. They're called Acrobot and Minigrid. One is a very, very simple physics simulation. One is a 5x5 grid. Nothing special. And you probably can't read these, but you can probably see the orange markings. So the four most important hyperparameters on the left are really anywhere on the right, including this one. This is probably interesting for those of you who know supervised learning well. This is the learning rate. So the learning rate is far from the most important one on the left and has vanishingly low importance on the right. So basically, this is irrelevant. What that means is if you work on a bunch of supervised learning and are used to tuning that, there's often a heuristic where you say, okay, if it's expensive, if it's hard, I could just tune the learning rate and I'll be fine. There are no learning rate importance hyperparameters here. We have to really be sure of what we touch every time. And in principle, this sounds like a great setup for using AutoML. This is exactly the case we always pitch AutoML for, right? We have many hyperparameters, we don't know what to do with them, we don't know which ones are important. And in practice, that's not done. In practice, we see a lot of hand tuning, many grid searches, and little systematic work due to large evaluation costs that are compounded by actually tuning the whole thing for the paper. When I mean systematic, I really don't mean that there's nothing. There are papers, and those papers often also evaluate well. So this might sound a bit catastrophic. The problem is that there are many RL domains, and to compare each domain, you know this yourself, you want to standardize the search space, you want to look at the same algorithms, ideally, and you want to have similar budgets, all of that. That is often not happening because people are looking at this from the reinforcement learning perspective. They want to know, for my control problem, that is really this domain, where I have this specific setup, how can I make it work? They're not asking, how can I build a general AutoRL system that does this across domains? And this is where we have a really bad signal for our community, for this venue, of what works well. But we do have some attempts. So a very naive attempt, obviously, is to just compare against these hand-tuned baselines we see in papers. We did that last time. Hand-tuned here means grid search. Grid search that was more or less documented in two interesting papers. HBO in this case was done by Deb, so DE plus hyperband. Fairly standard, and we see in most cases this works really well, even though the budget of the grid searches was over 10 times that of HBO. So that's a great result. But there's a bad result associated with it, of course, and that's this one. And this, again, will look super confusing to you, but what you're seeing is you see two similar colors next to each other in bars, and those are incumbent and test evaluation, where we only change the seeding. So we evaluated on 10 additional test seeds. And here in the marked regions, where we see really significant drops, the biggest one of them being a drop of to a factor of, I think it was an 8 of the training performance of the incumbent performance, just by changing the seeding. And this is something that hasn't really been taken into account a lot. Again, because for each seed we add a lot of evaluation cost. This is really blowing up the cost of doing AutoRL for a paradigm that's already expensive. And thankfully, there are two approaches where you can get this cost down massively. And I think that's a really interesting entry point for AutoRL. The first one being the being HBO RL bench. You heard already about that today. That's of course great because this evaluation cost at least really falls away. And even the training cost falls away. You really just look up your results for a bunch of algorithms for a diverse set of environments. And you also have associated pre-run benchmarks, not benchmarks, baselines that make a lot of sense. So for example, you usually want to compare against something like random search, or even PBT and its extension PB2, those in the reinforcement learning space, is something a lot of people are very interested in. So you can really get started with this, check how your own method performs on it. And it is even dynamic. So if you have something that, as I said, is dynamic, which is very valuable in the RL space, that can even reuse some of the information of the training process, you can still make it work. But if you need a bit more flexibility, beyond the tabular setting, which of course in some ways is always limiting, right? There's also an even newer benchmark. So you might need to look this up in 2 weeks on archive or something, which is based on JAX. JAX is the thing that has been really shifting in the last 1 or 2 years. So I think that's why right now is a great moment to think about getting into AutoRL, because now we can be a lot faster in evaluation. We implemented our algorithms in JAX and then performed a subset selection to find a set of 4 to 5 environments in each set that really represented how the hyperparameter space looks like. So right now this is hyperparameter based, and hopefully this will include architectures in the near future. And with that, we got the speed up factor of 10 to 12, both for training and evaluation. And this is, of course, can be a lot more dynamic and have bigger search spaces if you're not constrained to a table. But I think what's really interesting now is because we had a bunch more domains in there. So for example, we had these grid worlds in there, which are nice because you don't get any signal until you finished. We see this. And this, I think when Marius, my supervisor, first saw this, was like, we can't put this in a paper because here we see a random search, we see SMAC with hyperband, so BO and Bob, basically, and population-based training, which we might ignore for now. And everything just looks very similar. I mean, yes, SMAC, the black box version of it doesn't look bad, but all the confidence intervals are overlapping. And if we combine it with hyperband, random search suddenly looks really good. We thought in supervised learning, this question was settled, right? Like there's even a report paper from a NeurIPS competition from a few years ago that says random search is outperformed in supervised learning, at least in HBO. Apparently, this is not the case. And I think that's a really cool signal. That means even if you've been working on these methods and feel like we're stagnating in a bit, you know, just fighting for a few percentage points, probably in reinforcement learning, there's a lot of space to be more creative, to, as I said, be more dynamic, try to incorporate information from the training run, of which we have a lot, and then ultimately also combine methods from different areas of AutoRL, trying to make environment design work with NAS, algorithm selection, and hyperparameter optimization. I think is a massive challenge. But if we can make that work, even just for simulation, I think it will make it massively easier to actually bring reinforcement learning to other applications in the long term. And with that, I think you can ask us your questions.